Hi, welcome back again. You know that latitude and longitude can be used to describe any point on the surface of the Earth using unique coordinates. Sometimes you're also interested in the height or depth with respect to the surface of the Earth, such as when considering the position of a satellite or a mine shaft. In fact, using these three coordinates, height, longitude, latitude, you can describe the location of any point exactly, and they will form the basis of the so-called spherical coordinate system, which is the topic of this video. Previously, you learned that you can use polar coordinates in 2 dimensions and cylindrical coordinates in 3 dimensions as new coordinate systems in order to exploit certain rotational symmetries. Similarly, spherical coordinates can be used to describe regions in 3 dimensions that possess some spherical symmetries. Let's take a closer look at these coordinates. We denote them by rho, theta and phi, although you should keep in mind that some books use a different notation. They are the natural equivalents of the height, longitude and latitude that you're already familiar with. In fact, rho is defined as the distance of the point to the origin. In the case of the Earth, that would correspond to measuring the height plus the radius of the Earth, which in a general setting is a more logical choice than measuring just the height. You're already familiar with the variable theta from cylindrical coordinates, as it measures the angle between the positive x-axis and the projection of the point onto the xy plane. On Earth, theta corresponds to eastern longitude. Of course, we measure theta in radians instead of degrees, and we use a plus or minus sign for our angle instead of using east and west. Finally, phi is the angle between the point and the positive z-axis. On Earth, phi corresponds to the latitude, but instead of measuring it from minus 19 degrees to 90 degrees, we set the North Pole at 0 radians, the equator at pi/2 radians, and the South Pole at pi radians. So how would you express a point xyz in terms of the spherical coordinates rho, theta, phi? Recall that we constructed cylindrical coordinates by expressing x and y in polar coordinates. Now, take a look at the triangle with sides r, z and rho you see on the screen. We note that the distance rho and the angle phi now take the role of the polar coordinates in the zr plane. So that means that we can write z as rho cosine phi and r as rho sine phi. Since we already know how x and y can be expressed in terms of r and theta, we find that x, which is r cosine theta, is given by rho sine phi cosine theta, and y, which is r sine theta, equals rho sine phi sine theta. Since rho is a distance, we should always have rho bigger or equal than 0. In addition, we assume the convention that theta is in between 0 and 2 pi, and phi is in between 0 and pi. So for instance, let's try to describe the point 3/2 square root of 3, 3/2 square root of 3, 3 in spherical coordinates. First, as rho represents the distance to the origin, we can use Pythagoras' theorem to find out that rho equals 6. Next, we can try to compute phi by inspecting the formula for z. This tells us that the cosine of phi equals z over rho. Since the range of the inverse cosine is the interval 0 to pi, and phi is exactly in this interval, we can take the inverse cosine to find that phi is pi/3. Finally, we can find theta by drawing a picture for the x and y coordinates, and we conclude that theta is pi/4. You should always draw a picture when computing theta, as you could be off by an angle of pi radians when using the arctangent. Notice that the z-axis plays a special role in spherical coordinates as the main axis of rotational symmetry. It might be a good idea to be careful which axis you pick as the z-axis. Just as we did for polar and cylindrical coordinates, we would also like to integrate functions using spherical coordinates. So let's consider a volume element in spherical coordinates. The sides of this volume element have a radial difference of d rho, an angular difference of the theta and the phi. we can approximate the volume of this element by the volume of a rectangular box with the same sides. The height of the volume element is d rho. The arc length of the side, which in the picture goes from the positive z-axis to the positive y-axis, is rho d phi. Finally, the arc length of the side following a circle in the xy plane is r d theta. So in terms of spherical coordinates, it is rho times sine phi d theta. In total, the volume of the element is rho squared sine phi d rho d phi d theta. So suppose we have a continuous function f and a solid region E that can conveniently be described in spherical coordinates. Following the same procedure as for polar and cylindrical coordinates, we find that we can compute the triple integral of f over E by plugging in the expressions for x, y, and z in terms of the spherical coordinates and multiplying the entire integrand by rho squared sine of phi. The factor rho squared sine of phi is called the Jacobian of the transformation to spherical coordinates. Let's close off with an example. Let E be the solid region above the cone z is the square root of x squared plus y squared, and in between the spheres x squared plus y squared plus z squared equals 1 and x squared plus y squared plus z squared equals 4. In the picture you can see a cross section of this region with the xz plane. If we want to integrate a function over this region, we should express the region in terms of spherical coordinates. The spheres can easily be described in spherical coordinates by the equations rho is 1 and rho is 2 respectively. For the cone, it's slightly trickier. Plugging in the expressions for x, y, and z in terms of the spherical coordinates, we can reduce the cone to the equation rho cosine of phi equals rho sine of phi, which then yields cosine phi equals sine phi. Since phi only takes values in between 0 and pi, this equality can only be valid if phi is pi over 4. So, in terms of spherical coordinates, the cone is described by the equation phi is pi over 4. At the top of the solid region, we have phi is 0, so phi takes values in between 0 and pi over 4. Finally, there's no restriction on theta, so theta can be anything in between 0 and 2 pi. So if we want to integrate the function z squared over this region, we should compute the triple integral of the function rho squared cosine squared of phi times the Jacobian rho squared sine of phi. This iterated integral can be computed as you are used to, and you can find the result on the screen. That's all. We hope you learned something useful, and we wish you good luck with the remaining exercises.